All right, so we had started a lesson on elementary matrices, and we said we were going to stop the video and we're going to pick up looking at how elementary matrices affect other matrices when you multiply by elementary matrix. The elementary matrix is going to be multiplied from the left side of the other matrix. So we're going to call this left multiplication by elementary matrices, this theorem. So how do we want to state this? We're going to say let A be an n by p matrix. So our matrices, our elementary matrices, are going to be n by n. So we're going to have an n by n matrix times an n by p matrix. So what happens when you multiply a permutation matrix times A? So multiplying the n by n permutation matrix remember how we wrote that? Pij, right? The permutation matrix was like Pij. On the left side, well, let me get rid of that. Come on. On the left side of A. So what do you think happens when you multiply a permutation matrix on the left side of a matrix A? It swaps the ith and the jth rows, not columns, rows of A. That's what a permutation matrix. So remember, the columns of the identity were swapped out to give you the permutation matrix. So when you take that permutation matrix and you multiply it on the left side of another matrix, it swaps out the rows. The rows, let me underline that, rows. We should probably give an example. Let's take, for example, P12 times the matrix A. So P12 would be something like what? Start off 1, 0, 0, 0, 1, 0, 0, 0, 1. And you swap the first and, right, this is the identity. This, you swap the first and the second columns. So I'm going to swap those columns. I'm going to get 0, 1, 0, and 1, 0, 0. Okay, there's P12. Now A, let's say A is something like A, B, C across the first row, D, E, F across the second row, G, H, I across the third row. Different ways you can write that. I'm going to write it this way. And so I'm looking for the product here of these two matrices. I'm going to take the first row and the first column entry. 0 times A is 0, plus 1 times D is D, plus 0 times G is 0. Okay, now we're going to take the first row, second column entry. Dot product those. I lost something, didn't I? Why does it do that? There we go. First row, second column. 0 times B is 0, plus 1 times E is E, plus 0 times H is 0. Okay. First row, third column. 0 times C is 0, plus 1 times F is F, plus 0 times I is 0. Okay. First row done. Now on the second row. Dot products. First row, first column. 1 times A is A, plus 0 times D is 0, plus 0 times G is 0. Okay. Second row, second column. 1 times B is B, plus 0 times E is 0, plus 0 times H is 0. And what next? Second row, third column. 1 times C is C, plus 0 times F is 0, plus 0 times I is 0. Okay, done the second row. Going on to the third row. Third row, first column. 0 times A is 0, plus 0 times D is 0, plus 1 times G is G. Okay. Now on to the third row, the second column. 0 times b is 0, plus 0 times e is 0, plus 1 times h is h. Okay. Finally, the last entry, the third row, the third column. To find that third row, third column entry, we're going to dot product the third row with the third column. We're going to get 0 times c is 0, plus 0 times f is 0, plus 1 times I is I. And here we go. We're going to simplify that. D down the first column. A, G, DAG. Down the second column. E, B, H, EB. And down the third column. F, C, I. Now, if you compare this to the original matrix A, let's go back and focus on A for a second. A was this guy that I'm going to make green right here, right? This was A right here. What's the difference between this blue matrix that we calculated and A? Well, notice that the second and the first row are swapped out, right? They're swapped out. Yeah, so that's what we expected, right? We multiplied by P12, right? The permutation matrix. So it swaps out the first and the second rows, right? Rows, not columns, right? Our theorem says it swaps out the rows. Okay, so we're not going to prove that. We just did a special case for 3x3s. Let's go into the second type of elementary matrix. Number 2. That was called the scaling one. What happens when you multiply coming from the left by a scaling matrix? So multiplying the n by n scaling matrix. We call that one what? Mi, m sub I of r, with r not 0. On the left side of A, that is going to scale the ith row of A by R. Scales the ith row of A by R. So basically you just multiply the ith row of A, the row, not the column, by R. Okay, can we do an example of that? Yeah, over here I'm going to do an example on the side. Okay, here we go. Let's say we take m, that's not good, m to a 5 multiplied by a matrix A. M to a 5, you start off with the identity, right? And then you multiply the second column of the identity by 5. So what does that do? That gives you what? 0, 5, 0 right there. Okay, so we're just going to update that. We're going to write 0, 5, 0. Oh, crap. It's not. There it goes. All right, we're going to multiply that by A. We're going to call A just an arbitrary A, B, C, D, E, F, G, H, I. We're going across the rows here. All right, so I'm going to start trying to figure out what this is. I'm going to make a big old set of delimiters here, big old pair of delimiters to put my matrix in. I'm going to take the first row, first column. I'm going to get A plus 0 plus 0 when I do that dot product. Okay, I'm going to do the first row with the second column. I'm going to get what? B plus 0 when I do that dot product. Okay, let's do the first row with the third column. I'll do the dot product. There you get C plus 0 plus 0. All right, first row pretty much done. We have to clean it up later, right? Let's go into the second row. There's the second row. I'm going to take the second row and dot it with the first column. We're going to get 0 plus 5D plus 0. All right. First row, second row, first column done. Now the second row, second column. They get 0 plus 5E plus 0 as a dot product. Now on the second row, on to the third column. Here we go. Second row, third column. we're going to dot product of what? 0 plus 5f plus 0. All right, second row done. Now let's go to the third row. I just deleted something here. All right, here we go. Third row, dotted with the first column. We're gonna get 0 plus 0 plus g. Now let's dot the third row with the second column. You're gonna get 0 plus 0 plus h. And let's dot product the third row now with the third column. 0 plus 0 plus I. If you simplify this, down the first column you get A5D, G, down the second column B, 5E, H, and the third column you get C5F, I. Okay, good deal. Good deal. So what I'm going to do, I'm going to look at my matrix A back here. I'm going to put a green box around it. I'm going to compare that to my matrix here that I just calculated. M25, that scaling matrix times A. How do they compare? Well, pretty much the same matrix, except M25 times A, you scaled, right? The second row of A by 5. That's what we expected, right? Because we had M25 of A, right? So we knew, according to our theorem here, that you take basically 5. Oops, I didn't write too well. No, that didn't write well either. Okay, so you basically take 5 and multiply the second row by 5. You scale the second row by 5, okay. Pretty cool. Okay, here we go. Here's a number 3. So what was our last? We had this permutation, elementary matrix. You had the scaling. Oh, you had the replacement, right? What do you think happens when you multiply the replacement matrix on the left side of A? Basically what that does is going to give you a new ith row. The ith row gets updated or replaced by r times the jth row plus the ith row. So let's write that down. So multiplying the n by n replacement matrix r ij of r on the left side of A replaces the ith row of A with r times the jth row of A plus the ith row of A. Okay, that's a mouthful. Let's actually do this. Let's do an example. Let's do R23 times A. How about that? So I'm going to take R23. Ooh, it's not writing in blue. There it goes. No, R23 of 5, let's say. R23 of 5 times A. So what's R23? R23, that means you start off with the identity 1, 0, 0, 0, 1, 0, 0, 0, 1. And in the second row, third column, where's that? Second row, third column. That's right here. You're going to stick a 5, right? Okay, so let's erase that and stick a 5. Second row, third column. Okay, and we're going to multiply this by a matrix called A. We're going to call this what? Little a, b, c across the first row, d, e, f across the second row, g, h, I across the third row. Okay, let's do some matrix multiplication. All right, here we go. First row, first column, dot product, A plus 0 plus 0. First row, second column dot product is going to be B plus 0 plus 0. First row, third column is going to give us C plus 0 plus 0. All right, let's go on to dot producting the second row with various columns. Here goes the second row with the first column. You get the dot product is 0 plus D plus 5G. Like 5G service, right? All right, now we're taking the second row and the second column. Dot product 0 plus E plus 5H. And finally, we're going to take the second row with the third column. To conclude our second row entry, we're going to get what? The dot product 0 plus F plus 5I. Okay, that kind of covers the second row entries. Now let's do the third row entries. Ooh, crap, I lost some stuff. That was supposed to be a 0 right there. Supposed to be a 5 right there. Okay, let's go back. Dot product. First row, sorry, third row, first column is going to give me dot product 0 plus G. All right, third row, second column dot product. 0 plus H. And third row, third column dot product is going to be 0 plus I. If I write that down, that's what? A, D plus 5G going down the first column, G. Second column is going to be B, E plus 5H, H. And the third column is going to be C, F plus 5I, I. Okay, so let's look at this matrix and let's compare it to the matrix A here. I'm going to put a green box around A. Well, I was going to put a green box around A, but it went haywire. There it goes. So what's the difference between that matrix, capital A, and our matrix down here at the bottom? What's the difference? First row is the same. The third row is the same. But look at the second row. The second row is basically 5 times the third.